Okay, so let's look at our first family of lipids. And this lipid is going to be commonly called a fatty acid. Fatty acid, 2 by 4, can't get through the bedroom door, right? You've all heard that, or at least I heard it when I was little, and I used to say it all the time because I was very mean and as a child. I redheaded, right? That's temper. So fatty acid is something that we need to look at and we need to start to dissect because this is one of our simplest groups of lipids that we can identify and become familiar with. So fatty, of course, is basically going to refer to organic in nature. So this is probably going to include some type of hydrocarbon. So some type of carbon and hydrogen based compound that is going to be organic as far as the backbone is concerned. So we should probably see some type of organic piece of the molecule. Now the acid portion of this name, this is going to refer to a carboxylic acid, because that is one of the most common acids in organic. And we know that a carboxylic acid is a COOH group. So with the fatty acid family, we are going to end up seeing a portion of the molecule that's very organic, very hydrocarbon based, and then we're going to see a portion of the molecule that has some polarity associated with it, that could have a charge associated with it, and this is coming from our carboxylic acid portion of the molecule. Same thing happened with amino acids, right? You learned amino acids, and there was an amino group and an acid group, and you saw that that acid group could lose a proton to give you a charged part of the molecule. And the same thing is going to happen here. So for instance, one of these fatty acids could be something like stearic acid. So STEARIC. And stearic acid is commonly found in your face creams. So the next time you go and you go through the beauty aisle because of those wrinkles that are showing up on your face, or because of those crow feet that's around your eyes, or just because you need some hydration, you're probably going to see stearic acid as a ingredient in those lotions. Why? We'll talk about the properties of fatty acids and what they do, but if you take a look at the structure for stearic acid, it actually has 18 carbons involved. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. I told you it was very organic based. It should have a carbon based backbone, and stearic acid is no exception. It is 18 carbons long, and at the 18th carbon we are going to see this COOH group that's existing. So COOH, that is there. So that's my carboxylic acid, hence the acid portion of the fatty acid name, and then I find out that this is attached to a very long carbon backbone of the structure. So this is just one fatty acid out of many. However, what you will find out upon further investigation of fatty acids is that number one, they are actually even numbered. So that means that we will see carbons of 18, carbons of 20, carbons of 14, carbons of 12, but we really don't see carbons of 13. We don't really see carbons of 23. We don't see an odd number of carbons in these structures, and there is a reason, and we will talk about that reason, but for now this is a property that we can associate with fatty acids. They do have even numbers, and they have even numbers because of a very special reason that we will see in the next few minutes or in the next video. If you want to kind of take a look at some of these other examples of these fatty acids that are included, well, you will have a list of those. And the list is going to look like a chart similar to this one in your textbook. So up at the very top, you will see what we call saturated fatty acids. They're called saturated because they're all single bonds throughout. So we see lauric acid, and we see myristic acid, we see palmitic acid, stearic acid, and arachidonic acid. And all of these acids basically have an even number of carbons, 12, 14, 16, 18, and 20. Now, if we just take it at face value, this structure we should be familiar with because this is a carboxylic acid functional group. So that means that I can use the rules of carboxylic acid nomenclature and name these groups and these compounds just as I learned last semester. So the lauric acid and myristic acid, those are the common names that are associated with these groups. However, if I take a look at 12 carbons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12 total, we said back during the carboxylic acid group and carboxylic acid lecture module that 12 carbons was called dodec. And if this is a carboxylic acid, we use the word oleic acid at the end of the name. And those rules do not change because, let's face it, this is a carboxylic acid functional group. This is a carboxylic acid molecule. That's all that it is. It's just an extra long one. So it's no longer your butanoic acid or your pentanoic acid or your hexanoic acid. These are 12, 14, 16, 18, 20 carbons long. So they do have systematic names that come along with them. Dodecanoic for 12, tetradec 14, hexadec for 16, octadec for 18, and ico is 20. So we can call these with the IUPAC or systematic names if we want, but because we're really dabbling into a little bit of biology, just like we had common names for sugars, just like we had common names for amino acids, we have common names for fatty acids and lipids as well. So we really kind of train ourselves to learn the common names associated with these fatty acids and not the systematic name. Do I want you to memorize that stearic is 18 and myristic is 14 carbons? And the answer is, of course not. I don't want you to memorize these, but I do want you to know what a fatty acid is and what it looks like as far as shape and structure goes. Now, the second half of this table down here at the bottom, this is what we will call unsaturated fatty acids. And unsaturated fatty acids are just that. The molecules are unsaturated, meaning that they have double bonds associated with them. So all of these are single bonds all the way through. However, all of these down here below are double bond character. So we see 16, it's not palmitic acid, but palmitoleic acid. And if I want to give that a systematic or IUPAC name, it looks like there is some stereochemistry here at carbon number 9. So let's figure out where that comes from. If I start from here, carbon 1, 2, 3, 4, 5, 6, 7. And if I start from the carboxylic acid end, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So the 9 position, 9Z, that is from the carboxylic acid end. Again, this makes sense because during the carboxylic acid lecture module, you learned that this is carbon number 1. And because that is carbon number 1, that is what's going to define where the double bond is going to be located, and that's at carbon number 9, which is right here. They put Z because Z groups are on the same side, right? You have to speak German, kind of, or fake German, in order to memorize that or to remember that. But Z groups are on the same side basically means that this is a cis notation. So the groups are on the same side, meaning that on this carbon, hydrogen is sticking up here at the top, and on this carbon, carbon 10, hydrogen is sticking up there at the top. And the hydrogens are on the same side, so it's cis in a way. However, we can also refer to these long hydrocarbon chain groups as being on the same side as well. So if you want to regard this big long chain pointed down, this big long chain pointed down, then that is, by definition, the cis form or the Z form. Now, because these two carbons have hydrogens here, you might want to use cis and trans. If you want to use that, I'm okay with it. We said as long as hydrogen is involved into the conversation, you can use cis and trans. And each one of these carbons has a hydrogen associated with it. But we start to use E and Z more often. We kind of want to travel in that direction anyway, and that's why you're seeing those show up in the name. Well, oleic acid is actually the same structure, but it's an octadecanoic. It's 18 instead. So there's still a double bond at carbon 9. It's still the cis position, or the same group on the same side, the Z formation. The only difference is that it has some extra carbons out here at the end. Well, if I look at linoleic acid, we see two double bonds in here. We see a double bond here at carbon 9, and then we see another double bond at carbon 12. Both of those, again, are the Z formation. If I look at linoleic acid, I see three of them. Carbon 9, Z formation, carbon 12, Z formation, carbon 15, Z formation. If I take a look at carbon 20, arachidonic acid, I see four double bonds. Look at how this structure is drawn. One at carbon 5, one at carbon 8, one at carbon 11, and one at carbon 14, and all of those are the Z formation again. And then finally EPA, what we call EPA. Where does EPA come from? Icopentane, because we're looking at 20, and there's 5 double bonds, and the word acid. So carbon number 5, number 8, number 11, number 14, and number 17, I see a double bond. Hence, double bond character, alkene character, and we see a long carbon hydrocarbon chain, at least, coming off of that COOH group. Something else I want you to look at, comparing saturated to unsaturated hydrocarbons, or these fatty acids, is that look at what happens in the saturation of the carbons. If the molecule is saturated, and if the molecule extends that hydrocarbon chain, look at the melting point. Lauric acid starts off with a melting point of 44. We add more carbon, our melting point goes up. We add more carbon, the melting point goes up again. We add more carbon, melting point goes up again, and finally we add more carbon and melting point goes up again. So that is a general trend that we need to kind of learn as far as the world of fatty acids go. As your chain extends, as the molecule becomes bigger and bigger and bigger, then your melting points become larger and larger and larger as well. And it's all due to intermolecular forces. These intermolecular forces are basically going to come in and tell you that the more they overlap and the more they touch and the more cigar-shaped that they are, the higher the melting point. Look at what happens, however, with the unsaturation. As we get longer and longer carbon chains, the melting point in the beginning starts to go up, and then it plummets for some reason. Why is that happening? Is there a role, or is there something weird happening with unsaturated fatty acids? And the answer is no. we need to take a look not at carbon chain here, but we need to take a look at double bond characteristic. What is going on with the molecule to make that melting point lower? And that's what we will talk about in the next video. So stay tuned. Don't end it now. You've got another at least 10 to 15 minutes to do before you hit the stop button.